We have seen, with expanded centrifugal force, a mass body remains in its state against all forces that influence its direction of movement perpendicularly. According to the persistence of speed, the body defends against the external force that acts to and against the direction of movement of the body. Both together encompass three dimensions of spatial directions in which the moving body remains in its states against all external forces from all spatial directions, with the same mechanism and the same strength. This is how we summarize the expanded centrifugal force and the persistent force and call them inertial force, or simply inertia, which is represented as follows. In the chapters Extension of Centrifugal Force and Persistence of Speed we have always assumed that the radius of inertia remains constant. Now let's take another example. Let us consider a body that moves with the speed v and an angle theta to the horizontal and a distance r to the external force. Assume, this speed corresponds to this equation. This means that the resulting centrifugal force would be equal to the attractive force G if the body were to move in the x direction. Because the inertia is always equal to the acting force, A theta is equal to the G theta. Because the inertia is always equal to the acting force, A theta is equal to the G theta. And the component of A theta in the y direction is as follows. On the other hand, the speed component of the body in the x direction is the same as the following. This creates a centrifugal that is directed outwards in the y direction. Then the inertial force opposing the external force G is equal to the sum of equation asterisk and double asterisk. This is the same result as if the body were moving in the x direction at the same speed. As a result, this means that the inertia that opposes the external force is independent of the direction of movement of the body. In particular, when the angle theta equals 90 degrees or minus 90 degrees, i.h. the body moves towards or against the external force. In such cases the inertial force is equal to the square of the current speed divided by the current distance. An example. We also learned at school how the trajectory of a throwing stone can be calculated. For example, if you throw a stone horizontally from a roof terrace, the stone will fall to the ground after a period of. We may also know that this method of determining the trajectory only applies to speeds that can approximately be reached by hand throwing. This method no longer applies at higher speeds. And the deviation of the calculation result from reality is greater, the higher the speed. For example, it is no longer suitable for a fired bullet using this method. At a certain fast throwing speed, this method then fails totally. The reason for this is that in the method learned in school, the inertial force was not taken into account, which a body applies with every movement and always withdraws part of the gravitation. Because every moving body has inertia, the gravitational pull of the Earth is more or less withdrawn. Therefore actual Earth gravity for a moving body is one inertial force less. Therefore, effective Earth gravity for a moving body is one inertial force less, and the fall time of the throwing stone can be calculated as follows. If the throwing speed increases to about 7.9 km per second, the inertia is about 9.81. Then the gravity of the Earth is completely balanced and the fall time is infinitely long. We see, the difference between the results with and without inertia is enormous. So a moving mass body has an inertial force that opposes all external forces in order to persist in its states. Conclusion. The speed of a body accelerated by a is limited to a body m moved with v has an inertial force that is proportional to the square of the speed and inversely proportional to the distance. In order to be able to change the states of a body moved with v, a force F greater than the inertia of the body is required. The inertial force is always directed against the acting external force and is always the same strength as the respective external force, but at most, in the formula of the acceleration. The inertial force is independent of the shape and direction of the movement. The radius of inertia is the distance to the respective external force. It is quite certain that inertia must exist with every moving mass body, more or less. However, this basic physical knowledge has been completely neglected by previous physics. We have already seen that the difference between the results with and without inertia could be infinite. It is therefore very worrying when one thinks that all previous physical theories lack this basic knowledge. Thank you very much for your attention. See you next time.